Okay, so we have our floor splitting algorithm, and now we're ready to actually see the fruits of our labor and draw some of these floor nodes, or rather all of them, on the grid. So what we're going to do is we're going to go into our floor class. So we're going to add a couple of functions for drawing the nodes. So let's do a function, void draw floor nodes. And because the debug draw functions require a uworld, we're going to need to pass that in. So we're going to be calling this from an actor, which is basically our procedural room. And so we're going to need to pass in the uworld. We'll say world, like so. And we're going to do void draw floor node. And this will be for a single node. This will also take a uworld. World, and it'll take f corner coordinates called coordinates. Now, because we're using f corner coordinates here, we're going to need to actually include the floor node class. So include floor node.h, which is okay because it's a small class, it's a small header. We're going to include that here instead of forward declaring. So let's get rid of that forward declare, and now that struct will be defined. Okay, so let's go ahead and we can define these functions. So I'm not getting IntelliSense, so I'm going to go ahead and copy these, paste them into floor.cpp. I'm going to put them after the split vertical function down here. And I'm going to put floor, double colon, before their names. Give them function bodies. And let's go ahead and define these. So for draw floor nodes, well, we're going to simply loop through the partition floor and call draw floor node. So we really need to define draw floor node. So what draw floor node is going to do is it's going to draw debug line, right? So if we want to draw debug line, we need draw debug helpers. So let's include draw debug helpers .h, and we're going to simply call draw debug line. And this is going to take the world. That's why we put that in as an input parameter. And we're going to need a line start and a line end. So let's make those. So let's make a const f vector. And let's make this line 1 start. And let's initialize it. So what is it going to have? Well, we're going to draw this floor node based on the coordinates from the upper left to the lower right. Those are the coordinates we have, and we're going to use those to draw a line. So the first line is going to be from the upper left to the upper right. And so all we need to do is pass in coordinates dot upper left x, and this is going to be actually an integer, but because these grids are not actually 1 unit across, they're more like 200 in this case, we're going to need a variable for the unit length. So let's go ahead and add a unit length variable to the floor class. So let's go to floor.h, and let's go down here and let's say float unit length, and let's set that in the constructor, and we'll just say unit length equals 200.f for now, and we'll use that. So it's going to be the coordinates will be upper left x times unit length. Now it's going to take a now that's going to be the x component to the vector. The y component will be coordinates dot upper left y times unit length. And the z can be 0.f. Now, why are we doing upper left y? Well, because this is the line going from the upper left to the upper right. And this is the starting vector, the starting point for the line. So that's the upper left point. Now the end is going to be the upper right. So let's make a const f vector. Instead of line 1 start, why don't we say upper left? And for this one, let's say upper right. This way it's a little more clear what we're doing. And so the upper right has the coordinates of coordinates dot lower right x, right? Because the lower right x is the same as the upper right x. It's the it's the x coordinate of the lower right point, and that's going to be times unit length. And then of course we're going to say coordinates dot upper left y, because this is the upper left corner, and times unit length, and we're going to use 0.f for the z. So this draw debug line is going to take a start of upper left. It's going to take an end of upper right. We'll make the F color blue. Persistent lines, let's say true, and for lifetime, let's say -1, and for depth priority 0, and for thickness, let's do, say, 2.5. Actually, that's a little thick, let's do 1.5. F, like so. Okay, so that's drawing the line from the upper left corner to the upper right corner. Now we need to go from the upper left corner to the lower left corner. So let's go ahead and just define all 4 corners here. So let's do const f vector lower left. And that's going to be coordinates dot, and it's going to be the upper left x. And it's going to be times unit length. And then since it's the lower left, we need the lower right y. So coordinates lower right y times unit length, and the z will be 0. And finally, const f vector lower right. And this will be, the x will be the lower right x, and lower right y will be the y. So let's do coordinates lower right x times unit length, coordinates lower right y times unit length, and 0.f for z, and there we go. So we have the draw debug line for upper left to the upper right. We also want to draw a debug line from upper left to lower left. Right, so that's upper left to upper right, upper left to lower left. We also want lower left to lower right. So let's copy this again. And let's do lower left to lower right. And then finally, we want upper right to lower right. Let's do upper right to lower right. And this function will successfully draw the floor node. So now what's left is for draw floor nodes, we need to simply loop through and call draw floor node on all the nodes. So we can do this by making a for loop int 32 from 0 to, and this is going to be int 32, we'll just call it I, and we'll say I is less than partitioned floor.num, it's the number of elements there, and I++. And so what are we going to do? Well, we're going to get the coordinates, f corner coordinates equals partitioned floor at I. I'm going to get that partitioned floor. We're going to call get corner coordinates, and we'll use that for our coordinates. And then finally, we'll call draw floor node, passing in world, remember that's our input parameter for the function, and coordinates. So now we have a function that will loop through and draw all the nodes in the partition floor. So what's left to do is just go to procedural room after we've partitioned the floor, and we can simply call the floor draw floor nodes. And we have to pass something in to draw floor nodes, right? Because draw floor nodes takes a UWorld. We don't need the class there in the C++. We do need to include the world header, however, include engine/world.h. We'll have that so that we'll know that UWorld is defined. In a procedural room, what will we pass in? We'll just simply call getWorld. That is a function on the actor class. All right, so now that we have our partition function, we're calling it, we've partitioned all the nodes, and now we have the stack called partition floor, and we're just simply calling draw floor nodes, which loops through every element in partition floor and gets the corner coordinates, passes those into draw floor node, which will then draw 4 lines to create that rectangle. All right, so let's hit play, and here's our grid. Now we have our floor mesh here, and because its origin is in the middle of the mesh, we need to set this, and because it's 1,000 by 1,000, we need to set it to 500 by 500. That way its upper left corner is at the origin of the world, so when we push play, then our grid is here over the floor mesh. And it looks like it's a little hard to see because we're drawing exactly at 0. So if we draw, or if we actually move this down, we could do that, that'd be easier. Move it down by, say, -10, and now you'll see that there is our grid, and you'll see that we have some nodes are split all the way down to 1 by 1s, some are not. And now we would like to actually see this in a little bit, well, let's get a little bit more information from this. If we want to draw this, right, and we want to see the order in which these nodes were created, what we can do is we can simply draw these. Instead of calling draw floor node, let's save that function for later. And inside here, let's paste these here. And instead of drawing the lines at 0, let's use I, and let's say I times 10.f. And what this will do is it will draw each node a little bit higher than the last node, because I is incrementing from 0 all the way up to the number of nodes. So each node will be drawn a little bit higher, so we'll get this stepping effect that will show us the order in which these nodes were created. So you can see here that the very first split node was here, the one at the bottom. And then next was this one, next was this one. And you can see that as the algorithm progressed, we split the nodes up all the way to the end here. And now you'll see that most of these nodes are split all the way. I mean, it looks like the chances of being split are pretty high. And so we can affect this by taking a look at our basically, we can take a look at our should split function, and we can affect the should split function by looking at the percent chance of split. So here, percent chance of split, we have the floor length divided by floor grid size, and remember, floor length, that is the length in the y direction. And so since our split percentage is pretty high, we can multiply this number by some factor. So we can create a factor here in floor.h. We can say float split chance, something like split chance, and then in floor.cpp, we can affect it. We can make it, say, 0.5. And then down here in should split, we can take percent chance of split, multiply it by split chance. And then we can change split chance if we want to change the percent chance of split. So now we should split roughly half the amount of times. Now before we continue this, why don't we increase the grid size? So instead of 5, let's do say 25 by 25 with a room min x of 1, unit length of 2, split chance is 0.5. Now let's go ahead and compile this, and now we have a bigger grid size. And now what we should see is this algorithm working on a larger scale. Okay, so there's the compilation. We can take this and scale it by, say, 10 by 10, so it's a lot bigger. And let's hit play, and we'll see now, here are a whole bunch of grids, and it's looking like we have a bias towards one direction. We have a bias towards what looks like the y direction. Okay, so we're clearly always splitting in the vertical direction. So let's take a look at our should split node function. And it looks like here in ESO vertical, the case of vertical, our percent chance of split, we're dividing a float by a float, but I accidentally put int32 here instead of float. So whatever we were getting here, it was always a number less than 1, and putting it into an int32 truncated it to 0. So this needs to actually be a float value. So not only does percent chance of split need to be a float, but also the dice roll variable also needs to be a float. Now I accidentally made that an int32 as well, which meant that we were getting some value between 0 and 1, and because it was less than 1, it was being truncated to 0, so we're always getting a 0. So we'd never get this return false, we'd always return true here, and we would always split. So now that we've fixed those bugs, now we should be able to actually split. And now you'll see that we get random splits here. So sometimes the splits are horizontal and sometimes they're vertical. And so we have some random results here, and our percent chance of split is multiplied by split chance, and if that's too low, if you want it to be split more, well, you can change split chance to something even greater than 1 perhaps. You might want to multiply it by 1.2 or 1.25, something like that, and then you'll get more, you're more likely to split. So let's go ahead and take a look at that. Now you'll see we have more splits. And so we can go back to our draw function, and instead of using this I to elevate each node higher than the last node, we don't need that anymore. We can simply just draw them all at the same level, and that would just be by calling draw floor node here. And as we hit play, you'll see that it's all on the same level. And you've got some nodes that are bigger than others, some are the minimum size, and we can actually take our floor parameters and make these bigger. So let's make this 25 by 25, and yeah, we could even make the unit length smaller, like 100, something like that. And as you play with these parameters, you'll see the algorithm produces different results. So here's a nice random layout here. You got some rectangles that are small, some are big. You'll see here we got one that was split all the way down to a 1 by 1, and so on. So yeah, this is an interesting algorithm. You can tweak the parameters to see if you can, get it to split more often or split less often. For example, I'd like to take this split chance and multiply it by, say, something like 3.f, and see if we get a whole lot more small rectangles. And here we go. Yeah, it looks like we're splitting a lot more. So that is the splitting algorithm. And so now that we have a splitting algorithm, we can now start to spawn items in random locations in each individual floor node. So here we have this floor node. If we were to spawn a random item or an item at a random location in it, it would be anywhere in the bounds here. Same with any of these. So you'll see that there are some locations, some areas that are high density, have a lot of small little nodes, and then some are less dense and they have wider areas of empty space. So this is good for spawning items. It's also one technique that you can use to create randomly sized rooms for a dungeon. And so we're going to spawn some items in the next video. If you like this algorithm, if you like the way that this was taught, and you want to see more material like this, go ahead and, if you haven't already, like, subscribe, hit the bell, and thumbs up. And we'll see you in the next video.